Okay, thank you. Today my talk is about a work that we've been carrying out with my colleague Lionel Cavin on the fish diversification patterns through deep time. So here I'm using the word fishes to include two main groups. First one the Elasmobranchii. So these are this is a group that includes all sharks raising skates and the extinct sister group, the hybridons. So these are cartilaginous fishes, quite diverse today, with about 1,200 species, which are mostly present in the marine realm. And the fossil record for this group is mainly represented by isolated teeth that they shed continuously throughout their life. The other group are the Actinopterygians. So these are red fin fishes with a bony skeleton, extremely diverse today with 28,000 species, which is about half of the modern vertebrate species diversity. And they are present in all aquatic environments, and their fossil record is mainly represented by skeletons. Okay, sorry. So, the main issue that we've got when we try to identify paleodiversity patterns is that the sampling is uneven for any biological group. And this is due to several factors, that we can see some of them here: geological processes, fossil size, geographic distribution, preboreal processes, fossil composition, habitat fossilization, and so on. So all these factors and many others will end up in an incomplete fossil record for any biological group, and just looking at standing diversity may not reflect genuine patterns. So we've got to use analytical approaches to just bypass all these fossil record biases. And one of the possibilities for doing this is to use congruence methods that compare two sets of independent data. First, phylogenetic hypothesis, so it's really three topologies, and the fossil record of corresponding terminal taxa, which consists of the first appearance date, the FAD, and the last appearance date, the LAD. And the idea is that two sister taxa must have the same first appearance date, and when this is not observed in the fossil record, where it's almost never observed in the fossil record, some artificial range is added, which we call ghost ranges, just to fit the phylogeny. And then there's a variety of metrics that have been developed to assess the completeness of the fossil record on the basis of these calculations. I'm not going to explain those details here. We use the GAR and the MSN. But what is more interesting here is not really those metrics. It's rather than doing this, we compute first appearance dates that fit the phylogenies. So there are modifications that have been added to these methods that take into account the uncertainty in the FADs. So the problem is that we never get a first appearance date in million years. We most of the time have a stage. At best it's a substage, sometimes it's even a range of stages. So what we've done is we've made replications to pick an age within the age range of the first appearance date for each taxon, and this provides ranges of congruence scores. The other issue are polytomies in phylogenies. So what we've done is we've resolved those polytomies in two ways. First way is chronological, where we've taken the taxon with the oldest FAD within the polytomy and resolved the polytomy in chronological order. And we did the reverse, putting resolving the polytomy in reverse chronological order, where we took the taxon with the youngest FAD and resolved the polytomy, putting in this taxon the base of the pectinate clade, and so on. So all these provide ranges of congruence scores and corresponding computed FADs. So we've applied this to our data. So we've used several competing phylogenies, including all extinct and extant families. So we've got 95 families for Elasmobranchii, and 473 families for the Actinopterygii from the Upper Jurassic to the recent, and from the Triassic to the recent for Elasmobranchii. We also did this for the genus data, but I won't have time here to go through this. I'm going to stick to the family data. So the first result is that there's all the congruent scores overlap, which means that the minimum score for one phylogeny is not higher than the maximum score of another phylogeny, which means that it's impossible to spot a phylogeny that is significantly more congruent than others. And same for Elasmobranchii. But what is interesting here, again, is not really this, is rather that we've computed FADs that sort of compensate for the fossil record biases. So what we can do then is compute phylogenetic diversity, so it's the diversity that include the ghost ranges. So this is what we've got for Elasmobranchii. We've got here the standing diversity, and here the phylogenetic diversity range, with each curve corresponding to a phylogenetic hypothesis. And between the two, we've got the gap in the fossil record. So this is the stratigraphic range that we've added to fit the phylogeny. And same for Actinopterygii. And what we can see is that the gap in the fossil record for Actinopterygii is much higher. Much larger than for Elasmobranchii, which means that Elasmobranchii must seem to have a better fossil record. But if we want to look at diversification more precisely, we can work at origination and extinction rates. So I'm not going to comment on each diversification event here, but just spot some of the most important ones. We've got the early and middle Jurassic diversification for Elasmobranchii, and late Jurassic diversification for Actinopterygii, and in the Cenomanian for both groups, and in the Palaeontological for both groups as well. So one of the interesting things with this method is that we can, the taxonomic information is not lost after the analytical treatment. So we can identify the taxons that are involved in the diversifications. So for example, in the early middle diversification for the Elasmobranchii is mostly stem cow sharks, some carpet sharks, bullhead sharks, cat sharks, angel sharks, and few batteries clades. For the Actinopterygii in the late Jurassic, it's mainly those guys here, the Pycnodontiforms, that are involved in the diversification, along with some Helicomorphs and Elopomorphs. So if we want to try to think about what may have favored those diversification, we must look at what's going on in the Jurassic. Well, we've got continuous fragmentation of the Pangea, which creates continuously new ecological niches, both in the marine and freshwater realms. And for the early Jurassic diversification of Elasmobranchii, this follows the Triassic-Jurassic extinction that mainly hits hybodonts and other marine vertebrate groups. And in the late Jurassic, for the Actinopterygii, we also have a huge diversification of scleractinian corals, which probably favor the diversification of Pycnodontiforms, which were adapted to these environments. So the other diversification is in the Cenomanian. If we look a bit closer to the diversifying groups within Actinopterygii, it's mainly the teleosts that are involved in the diversification and the non-Percomorph teleosts, and mainly those guys here, the Acanthomorphs. And there's a paper that's been published in 2009 by Faro et al., and they identify this teleost diversification as the second biggest diversification among vertebrates. And they link this to a whole genome duplication, which is a bit hard to test actually, but we've tried to look at what what other factors may have favored those diversification. So we still have fragmented continents in the Cenomanian, but we also have very high sea levels, which provide very shallow water environments for epipelagic seas. And we also have very warm ocean temperatures, which are known to increase metabolic rates and promote speciation. But there's a series of papers that have been published recently that have shown that for Actinopterygians, warm ocean temperature have a negative effect on the egg and larval planktonic phase duration for this group, which means less dispersion and so more speciation. And the last diversification is in the Palaeontological. So if we look now what's going on within Actinopterygian, now it's still within Teleos, but it's the Percomorph that diversified in this period. It's a huge diversification here. And among them, it's the eukaryotes that are mostly involved, including lots of coral reef fishes. So if we go back to the Alpha Rose paper, they identify this diversification as the biggest diversification among in the vertebrate evolutionary history. So again, what is interesting is this diversification again matches very extremely high ocean temperatures again, but also this corresponds to the appearance of modern coral reef ecosystems in the Palaeontological, which provides new ecological systems and new food webs, especially for eukaryotes. So I don't know if I still have time. Yeah. All right. So, well, we've seen the conclusion that this method can be used to any biological group as long as you have phylogenetic hypothesis and fossil record. So we've seen that there's no fish phylogeny that can be identified as more concurrent than others, and the Elasmobranchii fossil record seems more complete than for Actinopterygian. And the interesting thing is that diversification events mainly match very high global temperatures, develop epicontinental sea and fragmented continents, but also the appearance of Scleractinian and modern coral reefs for Actinopterygian, one in the late Jurassic and one in the Palaeontological. And thanks for your attention.